good afternoon and welcome to this class on neuroscience of human movement. So, this is part 11 of our discussion on primary motor cortex. So, we have been discussing cortical areas that are responsible for movement generation, movement control, and we discussed whether what particular aspects of movement are being controlled by the motor cortex, what are the various other regions other than the primary motor cortex that are involved in motor function, such as supplementary motor area, premotor areas, dorsal ventral premotor areas, etc., all these things. And then we have also been discussing what are the various aspects that could be controlled by these areas, such as forces, the magnitude of force, directions, etc., and directions during movement, direction of force produced in an isometric object, etc. This also we discussed. We have also discussed what could happen if there is a lesion or if there is some accident that causes damage to these areas, what could happen. In the last class we discussed the differences between lesions of the upper motor neurons and lesions of the lower motor neuron. We will continue that discussion and in this class we will particularly focus on the fact that the motor map is dynamic and adaptable. So, when you learn a particular motor skill, the motor map changes as you learn, as you unlearn and relearn, the motor map changes. Is that true? Immediately a question that would arise to you is wow, so are you suggesting that your brain is changing throughout your life? The answer is yes. Well, the rate at which it changes could vary as a function of age. Obviously, the rate at which this learning is happening and this reorganization is happening could be much faster at a younger age and could slow down, but the most important message is that it is possible for the older brain to also reorganize itself. So, when you are learning a new skill, when you are learning a new motor skill, this results in functional reorganization, but this also results in structural reorganization. So, when we say structural reorganization, we are talking about actual changes, structural changes in the brain. So, that is a new hot topic that is exciting. Why? Because it provides us an opportunity to use this to rehabilitate, to improve function in people with compromised systems. This idea has received tremendous support in the recent years. One of the pioneers of this field is Dr. Mike Merzenich. Could check his works since 1980s. A pioneer, he has worked on this topic for several decades, and his work is considered as seminal for improving our understanding of this dynamic reorganization that happens in the brain, also called as neuroplasticity. So, now a hot area of research is this neuroplasticity driven approach to neurorehabilitation. After a lesion, how there is rearrangement or reorganization that is happening. This is studied very well by John Donoghue and his colleagues, and then how adaptation happens to an external force field. There are several methods in which this has been studied, how changes happen in the system. One particular approach is the external force field approach. We will discuss, so we will briefly touch upon these points. So, those who are interested must explore more and learn more. The idea is to give some examples of these approaches. Okay. So, let us take one approach. This is called as use dependent plasticity or activity dependent plasticity. So, what happened? So, they use Randy Nudo and his colleagues working with Mike Merzenich used monkeys and recorded while they are learning a skill. The topic is the activity is relatively complicated from a monkey's point of view. They have to pick small treats or candies from relatively small wells. They will have to use the thumb and the index finger or precision grip. Here I have a glass, this is relatively big. Assume that this is a small well. From this I have to put my fingers and then pick a treat and then eat, right. So, if I am a monkey, that is. So, but if the monkey is picking up from the small well, that means it requires to very fine skill to pick this up. Initially it is not good at this, as it practices more and more, it becomes more and more skilled at performing this fine dexterous activity. What happens? So, what they found was that before the monkey learnt this skill, the organization of the motor map, how did they find this? How do you know what is the organization of the motor map? Well, using the regular methods, we know what these methods are. In this particular study they use intracortical microstimulation, but we discuss these things. There are two approaches, one is stimulation approaches, the other is recording approaches, is it not? In one case we use microelectrodes to stimulate, this is called as intracortical microstimulation, and then in the other case they use microelectrodes to record from that, right. This we did discuss in previous class. In this particular study they used intracortical microstimulation techniques to stimulate different areas in the brain. Initially, before the monkey learnt this task, there was some area that was able to elicit movements of these effectors. After the monkey learnt this task, they found that the area which when stimulated the monkey performs this task, or the area that is dedicated for performance of this task expanded. So, in other words, there is physical expansion. In other words, there are other cells that was previously not responding to microstimulation in this particular manner, now they started responding in that particular manner. In other words, there is physical change in the cells. So, the area that was responsible, so that is what is represented. So, here you have some diverse areas, for example, those are more organized here, etc. So, those that are responsible for finger flexion, see they are here, now that is more, etc. So, this is one example of the actual picture. More examples, if you want to see more examples and more details, you should check this paper. This is from a adult squirrel monkey, right. So, journal of Neuroscience. So, as the monkey learned this task, the area which will cause this particular response actually expanded. So, if now I can stimulate a larger area, a broader area that will result in this particular activity. But now let us suppose that the monkey forgot this skill. We made the monkey unlearn this skill, or we make the monkey forget this skill, or after some time when the monkey forgets this skill, obviously its performance reduces. So, as you practice more and more, your performance is going to improve. That is obvious, we all know this. When you perform a motor skill, you are performing Bharatanatyam, you are performing a musical instrument, you practice more and more, there is going to be an improvement in this performance. So, that is well known. And if you stop practicing, right, your skill level is going to go down. Not clear how fast or how slow, but there is going to be some degradation in your performance. So, that is also well known and well accepted. So, no challenges there. So, obviously, when the monkey is not practicing picking up the food treat from the well for some time, and then we record, right, from its brain, it is now noted, or we stimulate its brain, and then we stimulate its brain. Now, the area that was earlier expanded has now come to a new state, now it has shrunk. So, that means of course, the performance has reduced. So, there are two things, one is functional degradation, the other is structural. Functionally, the monkey is no longer able to pick up the object as swiftly, as dexterously as before, or basically post practice it was doing so well, but after some time this practice related improvement has degraded. So, in other words, it has lost some of that skill. So, there is a degradation of performance, that is functional, but also the area that could elicit these movements has also shrunk. So, that is structural. Now, what does this say? This tells us what is the message from this study, and there are other studies that that accompany this line of research. This is one example. The lesson is that, as you use the motor function, as you perform an activity, plasticity or there is reorganization of the brain depending on the particular activity that is being performed. So, this is called as activity dependent plasticity or use dependent plasticity. Now, one other example of this is performed by Donoghue and his colleagues. Right. Now, this is in the, I suppose this is in the rat cortex, right. So, what they found was that there are two adjacent areas that are responsible for movement of the upper lip and the forelimb. So, what they found was that there are two lines of research. We will first discuss the first one. The first one is that there are two areas that are responsible for movement of the upper lip and the forelimb, and when they performed a surgical transection of the cranial nerve that controlled the upper lip, right. So, when there is a lesion that is caused, so I can no longer, so this rat can no longer perform movements of the upper lip because of a surgical transection. When this is done, what they found, within minutes stimulation of that area in the brain elicited movements of the forelimb. So, adjacent areas take over. So, that area that was responsible for eliciting the movements of the upper lip disappeared practically, and the other areas expanded. So, in other words, the other regions, other functions were represented in the region that was previously represented by the upper lip. So, that means this happened relatively quickly. This was so we are talking about less than 1 hour. So, within a brief amount of time, right. So, now earlier if you stimulate at that point, for example, you are going to see a response in the upper lip. If I stimulate that point, you are going to see a response in the upper lip. If you stimulate that point, you are going to see a response in the upper lip. Now, if you stimulate the corresponding points, I am going to draw that with a different color. If I stimulate corresponding points, that and that, for example, I am going to find response in the forelimb, not the upper lip. So, this change was very quick. So, this shows once again that the motor map is dynamic, and it happens, this dynamic change happens relatively quickly. We are talking about less than 1 hour, right. So, this is one message. The other message is that what they also found was that there were horizontal projections of motor function. So, this is the first study is showing reorganization after surgical transection, right, that is first. The second one, in the second case, what they found was that adjacent areas. So, if I stimulate particular neuron, they found that both the upper lip and the forelimb will respond. So, what they did was they came up with a method to block GABA. What they did was they injected bicuculin. So, bicuculin is a competitive antagonist of GABA receptors. So, what this does is it blocks it blocks the effect of GABA. So, they injected bicuculin into the forelimb area, right. So, that means GABA can no longer be GABA can no longer block, GABA can no longer inhibit any activity, because bicuculin is, as long as this is there, that effect is going to be blocked. After that, a stimulation of the forelimb upper lip area produced simultaneous movements of both the upper lip and forelimb, but before that, that particular area stimulation would produce movements of the upper lip only. So, what does this mean for us? This means that that particular area stimulates or causes simultaneous stimulation of the forelimb and the upper lip simultaneously, but movements of the forelimb were prevented by selective inhibition through GABA. Now, when I selectively block the GABA inhibition by injecting bicuculin, what is happening is that simultaneous activation takes place. So, this is the conclusion that they came with. This shows that there are horizontal projections from the motor cortex to multiple areas. So, once again showing that there are multiple ways in which this can happen, and there is sufficient amount of reorganization that happens. So, this is the work of John Donoghue. This work, this line of work has continued. So, this is 1991, and from that point onwards till date, tremendous amount of progress has been made in this field of how dynamic the motor map is, how adaptable the motor map is, how plastic that system is. So, yes, so let us continue this discussion. So, one other manner in which this can be studied. So, in general, studies of learning have involved several approaches. So, what is learning? Learning is the ability to improve performance through continued practice. One very crude definition of motor learning, for example, ability to improve motor performance through continued practice can be called as motor learning for the sake of this discussion. Now, multiple approaches have been used in studying motor learning. What are these? One is adaptation to force field. Now, note there are now instead of calling this as learning, I am calling this as adaptation. Adaptation means short term learning, adaptation to force fields. Visuomotor rotation, motor sequence learning, and then there are others. Okay. So, for want of time, I am not able to list all. There are many other approaches. At least two very popular approaches involve adaptation to force fields and visuomotor rotation. So, in this case, so what happens? What is adaptation to force field? Let us discuss that. So, a monkey is required to go from a center to a periphery, right, the usual center out reaching task, for example, right. Now, suppose when the monkey is making that movement, there is, so this monkey's hand is, or this monkey's arm is perturbed in sideway, for example. When would this happen in real life, you would ask? When would this happen in real life? Imagine this, when I am making a movement, when I am performing a reaching movement, when I am reaching to an object there, right, on the other side of the body, and I am turning my body and trying to reach. When I am doing that, my body, my hand is being perturbed in a very similar manner, right, because I am on the one hand I am rotating and I am reaching, right. But yet I am not feeling this as a perturbation. Why? Because it is my body that is rotating, and so the motor system knows how much I am rotating and accordingly sends, it is hopefully it is sending appropriate motor commands to adjust perturbations to that come out, or the non-intuitive perturbations due to the Coriolis forces such as this, for very brief amount of time, relatively small force, but these are well controlled and the response is considered relatively normal. Okay. But if the subject is not turning and simply reaching like that, suppose I am not rotating my body, I am just reaching like that, and when my arm is perturbed, and that perturbation depends on the velocity of the reach that I am making, then this perturbation is very unusual and it is somewhat difficult to learn to respond to that. Initially what happens is that early, so when I am reaching, when there is a perturbation, right, or this perturbation is performed in that direction, for example, I want to reach that point, that is the initial point, this is the destination, this is the destination, this is the starting point, right. You want to reach like that, but you are not able to reach like that because the robot is pushing you in that direction. So, you are like doing that initially, and that happens in all the directions, everywhere when I want to go like that, I am going like that, right. After some time what happens? After some time I am able to expect what would be the perturbation that will happen, that is that. I am able to predict what would be the perturbation that will happen and at what point it will happen, and I am able to produce relatively straight trajectories, right. So, the compensating forces are produced to overcome the effect of this perturbation. Now, suddenly when you switch off this perturbation, so after the person reaches this kind of straight trajectories, when you switch off the perturbations, what will happen is that there will be a compensation in the opposite direction, right. So, that means what? That means I have learned the perturbation that is produced by an external agent, right. So, the system is able to predict or is somehow able to expect what is going to be the effect of the perturbation that is going to come and is responding already. But then now in this case, this is the washout period in which I have switched off the perturbation. Because of this reason, I am producing it is as if I have been perturbed in the opposite direction. Initially the perturbation was in this direction, now the response is like this. After some time they produce straight trajectories, as one would expect. Neurons that responded during the early force period, whose directional tuning curve changed by about 15 to 20 degrees, and then there were other set of neurons that responded during the washout period, and then there were neurons that did not respond during both the periods, that continued common activity. So, these neurons whose activities do not change during various stages of learning are those that are responsible, are those that are probably governing the regular kinematics, as would happen when there is no perturbation, right. These neurons that respond during the early period are learning changing or appropriately changing the response in the early period, and then there are other neurons that learn during the late period and so on and so forth. So, this means so it is hypothesized that these neurons are responsible for learning and appropriately changing the behavior. So, the exact implementations of these are relatively controversial. It is claimed that there are internal models, there is this forward model that computes the future state of the limb based on efference copy, and then this future state of the limb is taken as an input by a different model, different internal model, which is an inverse internal model, which takes the future state of the limb and the expected errors to produce the appropriate motor commands that will generate relatively acceptable performances like this. It is unclear exactly how these are implemented, where these are implemented, what are the neuronal foundations, what are the neuronal substrates that underlie these models. It continues to be a controversial claim. However, this claim or this sort of thinking has become somewhat dominant within the field of motor control. We will not continue on the topic. Those who are interested can study and learn more about this. In the meanwhile, so this means motor learning is a form of learning that is not necessarily similar to learning of facts, figures, numbers, etc. this is what is called, or this is similar to what one would call as procedural learning. Okay. So, it was found, for example, in the case of patient HM. This is a very interesting story. Patient HM is the most famous patient in neuroscience. So, or HM is probably the best known single patient in the history of neuroscience. So, his case is very unique. Please do read this paper. Those who are interested must read this paper. It is available free on the internet. In his case, what happened was that he had very severe epilepsy in his 20s that caused Dr. William Scoville to perform a surgery that removed part of the middle temporal lobe. Okay. This caused a particular effect wherein this patient was not able to remember facts, figures, numbers, names, anything. So, it seemed like every day for him, every day was like living alone, every day was like waking from a dream, and every day was waking from a dream, and every day he is alone in itself, very unusual situation. So, this is like this patient would forget people who introduce themselves to him just a few minutes ago. So, if you introduce yourself to him, he will be like, hi, how are you, nice to meet you, and then a few minutes down the line he will ask, excuse me, we have never met, what is your good name, and you introduce yourself to him, and after some time he will again ask what is your name, because he is not able to remember facts and figures. So, Brenda Milner performed some experiments with this patient and found some very interesting results. So, what she did was she used a 5-pointed star, she used some motor skill that the person will have to, that this patient will have to learn by learning from a mirror, right. So, a mirror representation of the movement that he is making is shown to him, and he has to learn to perform this. And when he was presented this task, he claimed that he has never done this task in his life before, and he performed the task on the first day. And then when he came the second day, again he practiced the task, and on the day again he claimed that he has never done this task in his life before, and he performed the task. And on the third day, once again he came and he has claimed that he has never done the task before in his life, and he performed the task. As you would expect, that what you would expect is that since every day is a new life for him, every day is absolutely new for him, there would be absolutely no improvement in performance across the 3 days, because he also claims that he has not seen the task, he has never heard of such a weird thing in his life, he has never done it. He claims no conscious knowledge of this, yet his performance improved from day 1 to day 2 to day 3. So, that means there are substrates of learning, there are other forms of learning that are not necessarily located in that area. So, he is not able to remember facts and figures, names and numbers, but he is able to remember the particular motor task. Although he himself claims that I have never seen this task I have not seen, there is an improvement in performance. This gave rise to the idea that there are different forms of memory, different types of memory. This continued to be a controversial topic for a while, because convincing anatomical animal models of this were not present, were not available at that time. It was very difficult to verify these claims in animal models of this particular pathology, or induced lesions could not reproduce these results. So, this continued to be a very controversial area for a while, but now this is now well accepted. The point is that it is possible to learn without having, for example, an explicit conscious memory of having learnt. So, this gives rise to a whole new idea, what we would call as implicit learning or procedural learning. So, there are, for example, one line of research that I am pursuing in my lab, for example, involves learning that is embedded in, or subtly embedded within what appears to be a task. So, the subject we work with humans. So, the humans who participate in our experiments perceive a task as something, they perceive the task as task A, and they perform to improve in task A, but subtly what we do is we embed a different task, task B, in which they also simultaneously improve. Our goal is to study the improvement in the implicit embedded task. That is not obvious to the subject, but it is obvious to us as experimenters. We could strategically improve performance in specific things. So, this also goes along with this idea that improvement of learning happens in the presence of strategic variability. So, if I introduce variability, it is believed that there is going to be an improvement of learning. How? To what extent? These remain the open questions in motor learning. Those who are interested must read more on this topic. I will stop this discussion for now. We will discuss in future classes if there is time. So, in summary, we have discussed the work of Mike Merzenich and his contributions to at least to be introduced his contributions to plasticity research, and John Donahue's work, where they studied the particular areas that are responsible for different movements, and then Emilio Bizzi's work on force fields or adaptation to force fields. So, for his contribution for the discovery of mechanisms that allow experience and neural activity to remodel brain function, Mike Merzenich along with E. Marder and Carla Schatz were awarded the 2016 Kavli Prize in Neuroscience. So, what does this entail? So, what does this mean? What does this mean for us? The meaning is the following, that the brain continuously changes. How you view, how you experience a particular situation is determined by your brain, and what your brain is at a particular point in time is determined as the sum function as the sum of all your previous experiences. So, consider this duality. On the one hand, what you experience right now, that you are seeing this video, there are people around you or maybe not, there are objects around you, that experience shapes your brain, right. That experience is also is felt, or that experience itself is a product of your brain. So, this duality is an interesting duality in this field. So, the other example given by one of my colleagues is that suppose there is a river, consider there is a river that is taking this path, right, it is taking this path. So, these are the banks of the river that I am drawing. Let us suppose that this river is going, the water is flowing in that direction. There are two things. The direction or the path in which water flows is determined by the river, but also over a long period of time water also changes the river's shape, right. For example, it takes sand from one part to the other part, relatively small changes in the river's structure is made by water that is flowing. So, it is a two-way street, it is a dual arrangement between this. Similar to this is the case of how experience remodels the brain, how brain models the experience. So, this gives rise to the idea that it is possible, it is now possible to use a neuronal activity or to model and remodel brain function using neuronal activity or the neuroplasticity based approach to neurorehabilitation. So, with this we come to the end of this class. So, thank you very much.